We now shift our attention from finding confidence intervals for population proportions to finding confidence intervals for population means. And in general, there's a major question that we need to ask ourselves when we're finding confidence intervals for a population mean. The question is sigma known or not? Is sigma known or unknown? Depending on the answer to that and a couple of other important questions, you will soon. It will determine the technique we use for finding the margin of error E. Let's first review a few things. Recall, sigma is not any standard deviation. It is particularly the population standard deviation. Population standard deviation, not the sample standard deviation, for example. So we want to know, is the population standard deviation known or unknown in the problem? Also, we are now finding confidence intervals for the population mean. Recall that mu represents the population mean, and we use the point estimate x bar, which is the sample mean, to approximate it. And we build our confidence interval centered at the sample mean x bar. And then the confidence interval is precisely this, x bar minus e up to x bar plus e. So how do we compute the margin of error E when sigma is known? Well, it's not simply just when sigma is known. That's part of what we need. If the population standard deviation sigma is known and n is greater than or equal to 30 or the population is normally distributed, then we can conclude that the margin of error is z sub c times sigma sub x bar. Remember, z sub c is the critical value associated with the standard normal distribution for a given confidence level c. Also, sigma sub x bar is sigma divided by root n. What does this whole thing remind you of? Hopefully, it brings to mind the central limit theorem. The central limit theorem applied when the population standard deviation was known and you had either n greater than or equal to 30 or the population is normally distributed. Also, we're assuming that the samples are random. If you had a convenience sample, for example, this wouldn't apply. So we're assuming random samples. So basically, this technique we're about to develop is completely dependent on the central limit theorem. Let's quickly discuss the logic of this statement before we look at an actual example. So you need to have this population standard deviation sigma needs to be known. That must be true. And you have to have either this, n greater than or equal to 30, so sample size greater than or equal to 30, or the population is normally distributed. So this condition has to be true, and one of these two, population is normally distributed, or n is greater than or equal to 30, also must be true. Let's take a look at an example. A small randomly selected group of 35 hummingbirds has been under study in Arizona. The mean weight for this sample of birds is 3.15 grams. The population standard deviation of the weight of hummingbirds is known to be 0.33 grams. Find a 90% confidence interval for the average weights of hummingbirds in the study region. Interpret your results. So, can we use the central limit theorem here to find our margin of error E? Well, this right here tells us n is equal to 35, which is greater than or equal to 30. So again, we need to have either the sample size be greater than or equal to 30 or the data needs to be distributed normally. And it doesn't say the data is distributed normally, but you need to have that or the sample size be greater than or equal to 30. And we have that the sample size is in fact greater than or equal to 30. But we also must have the population standard deviation. And if you look here, the population standard deviation of the weight of the hummingbirds is known to be 0.33 grams. It specifically says that's the population standard deviation. So since we have the population standard deviation is known and our sample size is greater than or equal to 30, we can proceed to compute the margin of error by multiplying z sub c with sigma sub x bar. We are told to use a confidence level of 90% or 0.90. So we're going to compute the margin of error is z sub 0.90 times sigma sub x bar. And z sub 0.90, if you look at this critical value table that is in your formula sheet, you'll see for a c value of 0.90, the critical value is 1.645. And then remember, as was seen on the previous screen and in previous videos, sigma sub x bar is sigma, which that is this right here. So 0.33 divided by the square root of the sample size. The sample size is 35, so it's divided by the square root of 35. Now we can plug this whole thing into our calculator and get an approximate margin of error of 0.09. We can now form our confidence interval by subtracting e from x bar and adding e to x bar. Well, x bar is 3.15 grams. The mean weight for this sample of birds is 3.15 grams. So we've got 3.15 minus the margin of error of 0.09 equals 3.06. And x bar plus e is 3.15 plus 0.09, which is equal to 3.24. Our 90% confidence interval for the mean weight of hummingbirds is mu is between 3.06 grams and 3.24 grams. Again, remember, writing mu in here, not x bar, because I know x bar is in here. That's how we computed the interval. We're trying to make a claim about the actual population mean. And then, of course, we don't simply finish with that. We always need to interpret our results. So we've got to say what this means. So again, when we start with the level of confidence, we are 90% confident that our interval of 3.06 grams to 3.24 grams contains the population mean weight of hummingbirds. Now that we've completed this example, let's look at another conceptually important question. What happens to a confidence interval if you increase the level of confidence C? This is a very important question for fairly obvious reasons. For example, if you were to have surgery, would you rather your surgeon say that there's a 99% chance of success or a 50% chance of success? Clearly, 99% chance is much stronger. You'd feel much more confident about having the surgery done. So what happens to the confidence interval if you increase the level of confidence C? Technically, we already addressed this, that in order to have more confidence, you need to get more area under the standard normal curve. So that would make the interval wider. But technically, let's think about it with respect to this computation right here. Increase the level of confidence C, that's going to increase the size of the critical value, Z sub C. It gets larger as the confidence level goes up, the critical value goes up. That would then make the margin of error go up. So it would get wider. So you might be thinking, well, is there a way that we could possibly increase our level of confidence without having to actually make the interval wider? And the answer is yes. If you're going to make this thing bigger, which is always going to happen, the Z sub C is going to get bigger as C increases, we ultimately need to make this thing smaller to balance it out. And remember, sigma sub x bar is equal to sigma divided by the square root of n. So the way that we can make this thing smaller is by getting larger values of n, because you're going to divide by a larger denominator, which will make the overall fraction smaller. So basically, we can increase confidence without expanding the confidence interval by increasing the sample size. Let's take a look at an actual problem. As we just saw, another way to increase the level of confidence C that doesn't stretch the interval is to collect larger samples. So let's revisit this hummingbird scenario. So a researcher wants to estimate the mean weight of hummingbirds in Arizona. Determine the minimum required sample size to construct a 95% confidence interval such that the sample mean is within 0.09 grams of the population mean. The population standard deviation of the weight of hummingbirds is known to be 0.33 grams. So this is essentially set up the same as it was previously. We want a margin of error of 0.09 grams, but now we have a higher confidence level. Previously, we did computations with 90%. Here it's with 95%. So we're not actually constructing a confidence interval here. We're trying to find out what's the minimum required sample size to maintain our margin of error we found in the previous problem of 0.09 grams. If you were to take the margin of error formula, E equals Z sub C times sigma over root n. If you were to take that thing and solve for n, you would get this right here. Here we have a formula for computing minimum sample size. So we're going to use this to answer this problem. And there's a piece of notation here they may not be familiar with. This is not just a set of brackets right here. Notice that there's a little line at the top. This is called the ceiling function. And what the ceiling function does is it gives you the smallest integer greater than whatever your number is. And the reason we do this is because when you compute this, you might come up with n is 73.2811. So let's pretend that's what we came up with. N is 73.2811. But remember, n is representing a sample size. So n can't be a decimal. It needs to be a natural number. So since we're finding the minimum sample size, it has to be no smaller than this. We can't say the sample size is 73 because 73 is smaller than this. So we need to go up to the next nearest integer, which would be 74. That's how the ceiling function works. So let's actually do the computation over here and see how the ceiling function applies again. So we've got our sample size that we're looking for, n, is equal to Z sub C, where C is a 95% confidence interval. And if you refer to your critical values table in the formula sheet, you'll see Z sub 0.95 is 1.96. So we have 1.96 times sigma. Sigma is 0.33 grams divided by the margin of error here is 0.09 because we want the sample mean to be within 0.09 grams of the population mean. That means we're going to go 0.09 to the right or 0.09 to the left. So that is our margin of error, 0.09. And then, of course, if you look at this closely, we need to square that fraction and then take the ceiling of that. So we're going to square this fraction, and then we're going to take the ceiling of the result. So we are going to find the ceiling of the following number. We need to plug this whole thing with the parentheses appropriately placed into our calculator, and we get 51.65 approximately. Now, we're looking for the minimum amount, and we can't go down to 51 because that's smaller than that. So the integer immediately above 51.65 is 52. So the minimum sample size, if you want to keep all the same things that we did in the previous problem, but we want to increase the confidence level to 95%, instead of using sample size 35, which is what was in the previous problem, we need to get sample sizes of 52 or even higher if you wanted to.